Dimohon para hadirin untuk memenuhkan ruang kerusi hadapan dan kita akan mulakan majlis sebentar sahaja lagi. Dan sekali lagi diingatkan, para hadirin dimohon untuk mengaktifkan telefon di dalam mod senyap kerana majlis kita akan bermula beberapa minit lagi. Perarakan masuk Naib Chancellor Universiti Malaysia Sabah diiringi pengurusan tertinggi Universiti Malaysia Sabah. Hadirin dipohon berdiri. Hadirin dipohon untuk terus berdiri bagi nyanyian lagu negaraku dan Sabah tanah airku. hadirin dipohon duduk. Bagi memohon keberkatan dan keredaan Allah Subhanahu wa taala, majlis diteruskan dengan bacaan doa. Dijemput Al-Fadil Ustaz Ghazali Amirsan, pembantu Hal Ehwal Islam Pusat Islam UMS, untuk memimpin bacaan doa. Dipersilakan.
Al-Fatihah. Amin amin ya Allah. Bismillahirrahmanirrahim. Alhamdulillahi rabbil alamin. Wassalatu wassalamu ala ashrafil anbiya'i wal mursalin wa ala alihi wa sahbihi ajma'in. Allahumma ighfir lana dhunubana wa liwalidina warhamhum kama rabbayana shighara wa li jami'il mu'minina wal mu'minat wal muslimina wal muslimat al-ahya'i minhum wal amwati bi rahmatika ya arhamar rahimin. اللهم إنا نسألك سلامة في الدين وعافية في الجسد وزيادة في العلم وبركة في الرزق وتوبة قبل الموت ورحمة عند الموت ومغفرة بعد الموت. اللهم هون علينا في سكرات الموت والنجاة من النار والعفو عند الحساب. Ya Allah, ya Tuhan kami yang Maha Pemurah lagi Maha Penyayang, kami berhimpun pada hari ini berdoa memohon rahmat dan hidayah darimu. Semoga dengan rahmat itu Engkau berikan petunjuk kepada kami, Engkau perkukuhkan perpaduan kami, Engkau memperbaiki urusan agama dan dunia kami. Ya Dzal Jalali wal Ikram. Berkatilah majlis kami pada hari ini, Majlis Syarahan Perdana Profesor Dr. Rosalam Haji Sarbatly. Semoga dengan rahmat dan berkat yang Engkau limpahi ke atas majlis ini, dapatlah kami mengambil manfaat daripadanya. Allahumma ja'al jam'ana hadha jam'an marhuma wa tafarruqna min ba'dihi tafarruqan ma'suma. Ya Allah, Ya Rahman, Ya Rahim, gunakanlah perhimpunan kami pada hari ini, perhimpunan kami selepas ini, perhimpunan yang mendapat rahmat dan kampunan daripadamu, dan jadikanlah perpisahan kami selepas ini perpisahan yang mendapat keridhaan daripadamu. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina adzaban nar walhamdulillahi rabbil alamin.
Terima kasih Ustaz atas bacaan doa sebentar tadi. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Salam Malaysia Madani, salam Sabah Maju Jaya, dan salam 30 tahun UMS bertekad cemerlang. Yang berbahagia Profesor Datuk Dr. Kasim Haji Mansur, Naib Chancellor Universiti Malaysia Sabah. Yang berusaha Profesor Insinyur Dr. Rosalam Haji Sarbatly, Timbalan Naib Chancellor Penyelidikan dan Inovasi, pemidato syarahan kita pada hari ini. Yang berusaha Profesor Dr. Baba Musta, Ahli Lembaga Pengarah Universiti Malaysia Sabah, pegawai-pegawai utama dan kanan Universiti Malaysia Sabah, para kaki tangan, siswa-siswi Universiti Malaysia Sabah, rakan-rakan media, tuan-tuan dan puan-puan serta para hadirin sekalian. Selamat datang ke Majlis Syarahan Perdana Profesor Insinyur Dr. Rosalam Haji Sarbatly. Untuk makluman hadirin, majlis kita pada pagi ini juga disiarkan secara langsung dalam laman rasmi Facebook Universiti Malaysia Sabah. Para hadirin, majlis diteruskan dengan menjemput yang berbahagia Profesor Datuk Dr. Kasim Haji Mansur, Naib Chancellor Universiti Malaysia Sabah, untuk menyampaikan pengenalan pemidato pada pagi ini. Majlis dengan segala hormatnya mempersilakan.
Terima kasih saudara-saudari pengacara majlis. Bismillahirrahmanirrahim. Alhamdulillahirrabbilalamin. Assalatu wassalamu asrafil mursalin Sayyidina Muhammad wa ala alihi wa sahbihi ajma'in. Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi, salam Malaysia Madani, salam Sabah Maju Jaya, salam UMS, bertekad cemerlang. Yang berusaha Profesor Engineer Dr. Rosalam Haji Sarbatly, TNC Pendidikan dan Inovasi, kita punya pembedato syarahan pada pagi ini. Yang berusaha Profesor Dr. Baba Musta, Ahli Lembaga Pengarah Universiti Malaysia Sabah, pegawai-pegawai utama dan kanan Universiti Malaysia Sabah, para kaki tangan dan siswa-siswi UMS, rakan-rakan media, tuan-tuan, puan-puan serta hadirin yang saya hormati sekalian. Alhamdulillah, bersyukur kita kehadrat Allah Subhanahu Wa Taala kerana dengan izin limpah kurnianya kita diberi kesempatan pada pagi yang penuh dengan berkah, hari yang mulia pada pagi ini untuk bersama dalam Majlis Syarahan Perdana yang akan disampaikan oleh yang berusaha Profesor Engineer Dr. Rosalam Haji Sarbatly, Timbalan Naib Chancellor Penyelidikan dan Inovasi Universiti Malaysia Sabah. Sesungguhnya kita berada di sini dan berasa bertuah dan teruja pada pagi ini kerana sebentar lagi kita akan mengikuti syarahan perdana oleh seorang yang dikenali ramai sebagai pakar dalam teknologi membran dan nanofiber. Dan antara tujuan syarahan perdana ini ialah untuk menyebarluaskan ilmu kepakaran yang ada di institusi pengajian tinggi dan UMS tidak terkecuali. Jadi kita memang menggalakkan para profesor kita untuk tampil ke depan untuk mengetengahkan hasil penemuan daripada pendidikan untuk kita sebarluaskan dalam bentuk syarahan perdana, ya. Dan dengan pengalaman akademik selama 27 tahun yang diperolehi oleh yang berusaha Profesor Engineer Dr. Rosalam Haji Sarbatly ini, dalam beliau juga berkecimpung sebelum ini dalam industri kelapa sawit, dan Profesor Dr. Rosalam adalah penyumbang dalam aplikasi dalam rawatan air dan air sisa, pemurnian udara, kejuruteraan alam sekitar, sektor minyak dan gas serta kemajuan perubatan. Suka saya merakamkan ucapan terima kasih dan penghargaan kepada yang berbahagia Profesor Engineer Dr. Rosalam atas waktu yang diperuntukkan untuk menyampaikan syarahan perdana beliau yang bertajuk Sustainability in Membrane Technology sebentar lagi. Majlis Syarahan Perdana seumpama ini adalah satu tradisi, ya, akademik yang sangat signifikan bagi seorang profesor dan digalakkan sebagai menggunakan platform ini untuk menyebarluas ilmu. Seperti yang saya nyatakan tadi, sejak 30 tahun Universiti Malaysia Sabah, ya, ditubuhkan, kita ada beberapa syarahan perdana yang telah disampaikan oleh profesor-profesor daripada Universiti Malaysia Sabah. Dan kita pada tahun ini berkesempatan, ya, dan berpeluang mendengar seorang sahaja untuk tahun ini. Tahun lepas saya, kalau saya tidak ingat, Profesor Dr. Ismail Ali memberikan syarahan perdana, dan pada tahun ini Profesor Engineer Dr. Rosalam. Jadi kita mengharapkan pada tahun hadapan, ya, lebih ramai lagi para profesor BK7 kita untuk tampil ke depan untuk memberi syarahan perdana, untuk berkongsi ilmu pengetahuan kepada warga universiti dan masyarakat. Dan majlis ini juga biasanya kita anjurkan sebagai penghargaan, penghormatan, pengiktirafan kepada profesor, kepada seorang profesor sebagai pemikir yang telah banyak memberi sumbangan dan idea khususnya kepada dunia akademik, malah kepada negara, masyarakat secara keseluruhannya. Sebelum saya mempersilakan Profesor Engineer Dr. Rosalam Haji Sarbatly menyampaikan syarahan beliau pada pagi ini, saya berbesar hati untuk memperkenalkan siapakah individu yang bernama Rosalam Haji Sarbatly ini. Beliau dilahirkan pada 17 Disember 1968. Semalam menyambut hari jadi. Ya. 17 Disember 1968 di Kampung Pilaju Baru, Beaufort. Profesor Rosalam merupakan anak bungsu kepada 8 beradik kepada pasangan Tuan Haji Sarbatly bin Taib dan Saad Muhammad Tahir. Pendidikan awal beliau bermula di Sekolah Rendah Kebangsaan SRK Kelias Kecil, Beaufort dan Sekolah Rendah Agama Kelias Kecil. Beliau meneruskan pendidikan menengah di Sekolah Menengah Kebangsaan SMK Majakir, Papar, sebelum melanjutkan Diploma Sains di Institut Teknologi Mara ITM Perlis. Beliau memperolehi ijazah sarjana muda dalam kejuruteraan kimia dan proses serta ijazah sarjana dalam kejuruteraan alam sekitar dari Universiti Kebangsaan Malaysia. Profesor Rosalam memperolehi PhD dalam kejuruteraan kimia dengan kepakaran dalam teknologi membran dari University of Bath, United Kingdom. Beliau adalah jurutera profesional bertauliah Malaysia dan ASEAN. Perjalanan akademik Profesor Rosalam di Universiti Malaysia Sabah bermula pada tahun 1997 sebagai tutor dan seterusnya sebagai pensyarah kejuruteraan kimia pada tahun 1999. Diiktiraf sebagai salah seorang finalis Young Engineers Britain pada tahun 2003. Beliau berjaya menyelesaikan PhD dalam tempoh kurang daripada 3 tahun. Sekembalinya beliau ke Malaysia, beliau menubuhkan makmal penyelidikan membran di Universiti Malaysia Sabah yang kemudiannya diperluas menjadi makmal penyelidikan membran dan nanofiber pada tahun 2012. Peranan kepemimpinan beliau di Universiti Malaysia Sabah termasuk sebagai timbalan dekan dari tahun 2006 hingga 2007 dan dilantik sebagai dekan pada tahun 2007 hingga 2016 dan pengarah Pusat Penyelidikan Minyak dan Gas dari tahun 2016 hingga 2018. Profesor Rosalam telah menerima pelbagai anugerah berprestij termasuk Anugerah Saintis Sabah pada tahun 2023, Anugerah Khas Tun Chancellor Universiti Malaysia Sabah pada tahun 2023, Anugerah Pertandingan Projek Kelestarian ICAM Malaysia 2021 dan Anugerah Saintis Penyelidikan Terunggul Malaysia 2020. Beliau telah menerbitkan lebih daripada 100 kertas saintifik dan memegang 4 paten antarabangsa dalam rawatan air dan teknologi nanofiber. Kerjasama penyelidikan beliau melibatkan perkongsian dengan Zeta Limited Jepun dan Tokyo Institute of Technology dengan tumpuan kepada pengkomersialan produk berasaskan nanofiber maju seperti topeng muka, penapis air dan bahan serapan tumpahan minyak. Dalam beberapa tahun kebelakangan ini, beliau menubuhkan pusat penyelidikan nanobahan di Universiti Malaysia Sabah yang mempelopori inovasi nanoteknologi untuk menangani cabaran kompleks dalam penjagaan kesihatan, perlindungan alam sekitar dan aplikasi industri. Profesor Rosalam turut aktif menyumbang kepada pembangunan dasar, berkhidmat sebagai pengurusi jawatan kuasa penasihat kepada Menteri Pendidikan dan Inovasi Kerajaan Sabah. Beliau juga pernah menjadi penasihat kepada CEO Sabah Oil dan Gas Development Corporation atau SOGDC dan ahli sub jawatan kuasa model baharu, ekonomi baharu Sabah. Sebagai penyokong tegar sains terbuka, usaha Profesor Rosalam bersama program Erasmus Plus Kesatuan Eropah telah memainkan peranan penting dalam membangunkan dasar sains terbuka untuk Asia, menggalakkan ketulusan dan kolaborasi. Usaha ini membuka akses kepada maklumat saintifik, meningkatkan penglibatan saintis awam dan mewujudkan ekosistem penyelidikan yang dinamik. Komitmen Profesor Rosalam terhadap teknologi lestari dan kecemerlangan akademik telah memberi impak global dalam kejuruteraan kimia dan sains alam sekitar, meninggalkan legasi sebagai pemangkin inovasi dan perubahan positif dalam dunia akademik, industri dan masyarakat. Itulah latar belakang pemidato kita pada pagi ini, dan saya doakan semoga perkongsian ilmu yang akan disampaikan pada pagi ini memberi manfaat kepada warga Universiti Malaysia Sabah dan juga Sabah secara khususnya dan Malaysia secara amnya, dan juga menggalakkan kepada ahli-ahli akademik supaya terus tampil untuk memperkasa ilmu pengetahuan dalam bidang masing-masing untuk kita membudayakan kecemerlangan ilmu di Universiti Malaysia Sabah yang kita cintai ini. Sekian, wabillahi taufiq wal hidayah. Assalamualaikum warahmatullahi wabarakatuh dan salam sejahtera.
Terima kasih Yang Berbahagia Datuk Naib Chancellor. Dimohon Yang Berbahagia Datuk Naib Chancellor untuk kekal berada di pentas. Dengan ini, majlis seterusnya menjemput Yang Berusaha Profesor Insinyur Dr. Rosalam Haji Sarbatly serta pegawai-pegawai utama Universiti Malaysia Sabah untuk naik ke pentas bagi penyerahan buku syarahan pemidato kepada Datuk Naib Chancellor. Majlis mempersilakan. Terima kasih Yang Berbahagia Datuk Naib Chancellor dan Profesor Insinyur Dr. Rosalam serta pegawai-pegawai utama. Hadirin sekalian, marilah kita saksikan sedikit persembahan montaj yang mengisahkan tentang kehidupan dan pengalaman hidup pemidato kita pada hari ini. Sama-sama kita saksikan.
In the journey of life, like water flowing through time, every drop carries a story. This is the story of Professor Insinyur Dr. Rosalam Haji Sarbatly, a visionary who grew from a boy in the rural heartlands of Sabah to a leader in global innovation. Growing up in Beaufort, From a pious family with good virtues, where clean water was a luxury, young Rosalam witnessed firsthand the challenges of access to safe water. These early experiences shaped his determination to find lasting solutions to the problems of his community. As he ventured into the developed world of United Kingdom, pursuing Doctor of Philosophy in Membrane Technology at University of Bath, Professor Rosalam encountered groundbreaking technologies and ideas. Yet, he remained deeply connected to his roots here in Sabah, ensuring the innovations he championed would benefit those who needed them most. For nearly a decade, Professor Rosalam served as Dean of the Faculty of Engineering, transforming it into a powerhouse of innovation and academic excellence. Under his visionary leadership, the faculty experienced remarkable growth not only in infrastructure and student enrollment, but also in research output and global recognition. At one point, half of the total research grants awarded to University Malaysia Sabah was secured by the Faculty of Engineering, a testament to his strategic leadership and the trust funders placed in his vision. His ability to identify talent, nurture innovation, and inspire teamwork turned the Faculty of Engineering into a benchmark for other faculties at UMS, setting a new standard for performance and impact. Under his guidance, students thrived, researchers excelled, and the faculty became a beacon of hope and progress for Sabah and beyond. At the heart of his journey lies his greatest motivation, his beautiful wife and children. They are his muse, his unwavering source of strength, and his driving force to make the world a better place, not just for them, but for the university and beyond. Currently, Professor Insigne Dr. Rosalam stands as the Deputy Vice-Chancellor of Research and Innovation at University Malaysia Sabah, inspiring the next generation in academic platform while championing sustainable water solutions. His journey has turned challenges into opportunities for communities worldwide. Professor Rosalam introduced targeted initiatives to foster a culture of excellence among faculty members and students. He established research clusters, secured industry collaborations, and expanded the university's innovation programs. These efforts paid off tremendously. Just as water shapes the earth, our experiences shape who we are. Professor Insigne Dr. Rosalam's journey reminds us the flow of time may bring change, but with vision and courage, we can guide it towards a brighter future.
Demikianlah tadi persembahan montaj pemidato kita pada hari ini. Hadirin sekalian, majlis diteruskan dengan sesi bergambar dan dijemput semua hadirin untuk maju ke hadapan bagi mengambil gambar bersama-sama Datuk Naib Chancellor dan pemidato kita. Majlis mengumumkan Dato' VC akan meninggalkan majlis kita pada pagi ini kerana perlu memenuhi komitmen seterusnya. Terima kasih yang berbahagia Dato' Naib Chancellor kerana meluangkan masa bersama-sama kami pada pagi ini. Hadirin sekalian, tanpa melengahkan masa, majlis menjemput Yang Berusaha Profesor Insinyur Dr. Rosalam Haji Sarbatly, Timbalan Naib Chancellor Penyelidikan dan Inovasi Universiti Malaysia Sabah, untuk naik ke pentas bagi menyampaikan syarahan beliau yang bertajuk Sustainability in Membrane Technology. Dengan segala hormatnya, majlis mempersilakan.
Bismillahirrahmanirrahim. Selawat dan salam ke atas junjungan besar Nabi Muhammad sallallahu alaihi wasallam. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera, salam maju jaya dan salam Malaysia Madani. Terima kasih kepada saudari pengacara majlis yang berbahagia. Tadi kita ada Profesor Dr. Kasim Haji Mansur yang datang untuk meresmikan dan seterusnya memperkenalkan saya pada pagi ini. Yang berusaha Profesor Dr. Baba Musta, ahli lembaga Universiti Malaysia Sabah, para pengurusan tertinggi Universiti Malaysia Sabah, Profesor Madya Dr. Abu Zahrim Yasir, Dekan Fakulti Kejuruteraan, dekan-dekan, pengarah-pengarah dan semua anggota pengurusan UMS, para profesor yang dihormati, penyelidik, warga akademik, rakan-rakan, pelajar-pelajar dan para tetamu yang dihormati. Tuan-tuan dan puan-puan sekalian, izinkan saya menyampaikan syarahan perdana ini dalam bahasa Inggeris. A very good morning to all. I am deeply honored to stand before you today to deliver my inaugural lecture titled Sustainability in Membrane Technology. As an academic and researcher, these milestones is not just a reflections of my journey, but also a testament to a collaborative efforts of many colleagues, students, institutions who have contributed to the advancement of membrane science and technology. Today, I'll take you through the fundamentals of membranes technologies and focus on key innovations that bridge sustainability and practical applications. This lecture is divided into two main parts to provide a clear understanding of membrane technology and its application. The first part focuses on fundamentals, covering an introduction to membrane technology, the principle of membrane science, fabrication technique like phase invention and electrospinning, and the key processes such as filtration and distillations. While the second part highlight focus areas including the development of durable ceramic membranes, nanofiber for improving membrane performance, brackish water treatment using sustainable distillation system, and the integration of membrane with microalgae for wastewater treatment and biofuel production. Let me share my 27 years journey at University Malaysia Sabah, which I have dedicated myself to advancing membrane science and tackling challenges in water and wastewater treatment, energy efficiency, and sustainable technologies. My expertise in membrane technology focuses on four key areas: advancing water filtration, gas separation, and environmental protection, ensuring clean water and renewable energy, improving rural livelihoods and economics, and link research to policies for sustainable development. My research journey in membrane technology has achieved significant milestones in innovation and collaboration. After earning my PhD in membrane separation from University of Bath in 2005, I returned to Malaysia in 2006 to develop flat sheet membranes, polymeric membranes, and establish ceramic membrane processes in FKG lab. By 2007, I advanced to hollow fiber membranes fabrication, followed by breakthroughs in membrane distillation in 2010, securing 2 patents. So a collaboration with Tokyo researchers in 2012 expanded my focus to nanofiber material, including micro nanofiber for oil spill remediation. Between 2014 and 2016, I introduced microalgae membrane bioreactors for wastewater treatment, addressing issues related to Sabah's ammonia urea plant. In 2015, I and the industrial team secured RM 2.62 million from MOSTI for brackish water desalination. During COVID pandemic in 2020, my Japanese collaborators and I advanced gas separation membrane and nanofiber face mask with Zeta Limited in Tokyo Institute of Technology. Recently, I explored nanofiber for wound healing in 2023 and contributed to Asia Open Science Policy with Erasmus plus EU and 5 other partners countries in 2024. Together, this initiative have generated research valued at over than 6 million, significantly advancing science and society. As part of my journey, I published a globally distributed textbooks titled Membrane Technology for Water and Wastewater Treatment in Rural Region with IGI Global in 2020. The book summarized my research group advancement and application, serving as a key reference for student, researcher, and policy maker seeking sustainable water solutions. My research group applied membrane technology to address the rural community needs. We developed modular water treatment system for heavy metals removal, ensuring safe water and with the real-time monitoring. Nanofiber winding were integrated into surround design for sustainable heat and sound insulation, enhancing safety and comfort. Additionally, we introduced incinerator technology for managing small-scale solid waste like agriculture and garden waste. This innovation demonstrates how membrane technology improves rural livelihood. Let us explore the core of the lecture, membrane technology, covering its definition, classification, and transport resistance. A membrane is a barrier that allows certain substances to pass through while blocking others. In the diagrams, phase 1 with higher concentration and phase 2 with lower concentration are separated by the membrane, which controls movement of specific substances between the two sides. Membranes are classified based on their characteristic and application to meet specific needs. They can be categorized by material types like polymer, ceramic, and metals, and nature like biological, synthetic, organic, or inorganic. Their geometries may be flat, sheet, or tubular, with modules like spiral wound and hollow fibers. They are further classified by characteristics like hydrophilic or hydrophobic, structure like homogeneous and composite, symmetric like symmetric or asymmetric, and pore size like micropore, mesopore, and macropore. The transfer properties such as mechanism, pores and dents, and phenomenon, sieving or diffusion, as well as driving force like pressure and concentration gradients are also the key factors. One of the key challenges in membrane technology is transport resistance, which directly affect membrane performance. The first is concentration polarizations, where solutes accumulate near the membrane surface, reducing the driving force and overall efficiency. The second challenge is a membrane fouling, which occurs in four ways. The first is complete pore blocking. Solutes fully obstruct the membrane pores. Internal for blocking, which is solute adhere inside the pores, and partial for blocking, which some pores are blocked while others remain open. And cake formation, which is solute from a dense layer on the membrane surface. This resistance shows in the diagram is a membrane resistance. They call it fouling resistance, concentration polarization, reduced efficiency in increased operational costs. Managing this resistance is crucial in enhancing the performance, durability, and cost effectiveness of the membrane. The next section will focus on membrane fabrication, covering membrane modules and key fabrication techniques. Let's begin with the flat shape type module. The flat end frame module arrange membrane in a sandwich-like configuration. It is a packing density of 100 to 400 square meter over cubic meter, making it simple and effective for low capacity system. The spiral wound module wrap membranes around the central pipe with a higher packing density of 300 to 1,200 cubic square meter over cubic meter. It is widely used in water and wastewater treatment due to its compact design and high efficiencies. For cylindrical shaped membranes, there are three key modules. The first is the tubular model used non-self-supporting membranes arranged in a port tubes. It has a packing densities of less than 300 square meter over cubic meter and a tube diameter of more than 5 millimeters. The capillary modules consist of self-supporting capillary membranes. It offers a packing density of 600 to 1,200 square meter over cubic meter with a tube diameter of 0.5 to 5 millimeter. The hollow fiber modules contain a bundle of hollow fiber membranes loaded into a housing. It is significantly higher packing density of approximately 30,000 square meter of, over cubic meter and the fiber diameters of less than 0.5 mm. This module offers flexibility and scalability, making them suitable for application ranging from small scale system to industrial process. Here is an example of tubular capillary and hollow fiber membranes. Tubular membranes are commonly used in high fouling environments such as wastewater treatment, while capillary membranes are suitable for medium capacity filtration process like for instance, example is actually the blood cleaning. And hollow fiber membrane are widely used in a large-scale water treatment system due to their high packing density. The first key fabrication technique is phase invention, a process where a solid polymer solution separates into solid and liquid phases through demixing. This can be achieved through four main methods, which is immersion precipitation, where the solution is cast into a spot and submerged in a coagulation bath. Thermally induced precipitation, which involves dissolving polymers at high temperature and cooling them to separate phases, which is evaporation induced precipitation, where the solvent evaporates to form a porous membrane, and a vapor-induced precipitation where the solution is exposed to a non-vapor to trigger separations. These methods are crucial for creating membrane with tailored structures and properties. First invention for flat-shaped membrane. The first invention is a key method used to fabricate the flat-shaped membrane. The process began by separating a polymer solution evenly using a casting knife. This is followed by immersion in coagulation bath, where the membrane structure forms through phase separation. Post-treatment step then carried out to ensure the membrane stability and performance. For tubular membranes, the polymer solution is cast onto the supporting tubular structures and then immersed in a coagulation bath to undergo phase inversion. The hollow fiber and capillary membrane spinnerit techniques such as dry spinning, melt spinning, or wet spinning are used to produce uniform fibers. These membranes are self-supporting, offering both flexibility and high performance. The stretching method is a mechanical process for casting porous and crystalline polymer. It involves melting, extruding, and stretching the polymer to form a pore structure. There are two key types, which is they call it cold stretching, which create micropores, and hot stretching, which control pore size and distribution. This precise technique is essential for advanced filtration application, ensuring high performance and reliability. The trick etching techniques create precise membrane pores by exposing a non-porous membranes in ion irradiations, forming liner track. These tracks are then chemically etched to create uniform pores. This method allows control over pore size between 10⁻⁹ to 10⁻⁵ meter and the pore density between 1 to 10 over square meter, making trick etch membrane highly accurate, and they are widely used in medical filtration and analytical applications. Ladies and gentlemen, this section explores membrane process driven by pressure, temperature, osmotic pressure, and partial pressure, which are essential for effective separation and filtration, desalination, and other processes. The membrane process separates a feed mixture into a component using a semi-permeable barrier enabling selective movement based on specific properties. Key separation mechanism including first, size-based separation, which is retain larger molecule while similar one pass is sent in microfiltration and ultrafiltration. While the solubility in this diffusivity-based separations allow component with high solubility to pass in reverse osmosis, gas permeation, and also the evaporation. While charge-based separation, which separates charge species based on polarity, is in electrodialysis. This diagram shows the selective movement driven by force like pressure, concentration, or charge, essential for water purification, gas separation, and industrial application. Pressure-driven membrane process are categorized by pore size and operating pressure, providing solution for various applications. Microfiltration has a pore size of 0.1 to 10 micron, operates at 1 to 3 bar, and required minimal pretreatment and low cost, while ultrafiltration has pore size of 0.01 to 0.1 micron, operates at 0.5 to 10 bars, and required moderate pretreatment with medium capex and opex. While nanofiltration features a smaller pores, which is 0.001 to 0.01 micron, operate at 3 to 20 bars and need high pretreatment resulting in higher cost. While the reverse osmosis is the smallest pores, with between 0.001 to 0.01 micron, operate at 23 to 35 bars and required extensive pretreatment with the highest capping and opex. These processes are widely used in water purification, water treatment, and industrial application, offering tailored solutions for specific needs. Pressure-driven process use two main flow methods with distinct features. The first one, they call it dead end modes, which flow feed move perpendicular to the membrane surface. It is simple but prone to fouling due to cake layer formation, reducing efficiency over the time. While the cross flow mode, which is feed flow more parallel to the membrane surface, this minimizes fouling, maintains with better flux, and ensure higher performance over a longer period. As shown in the graph, cross flow mode significantly improves membrane performance for a long-term operation. Membrane distillation, use a temperature gradient to create a vapor pressure difference, allowing hot liquid to vaporize and pass through the membranes. Considering on a cooler side, it is energy efficient, operate at low temperature, and support renewable energy sources like solar or waste heat. This makes it ideal for desalination, organic purification, and producing high quality distilled water. There are 4 types of membrane distillations, each with distinct features tailored to specific need. The first one is direct contact membrane distillation. Both the feed and permeate side are in direct contact with the membrane. This is the simplest and most widely used type, ideal for desalination and simple application. While the air gap membrane distillations, a layer of air is introduced between the membrane and condensating surface. This reduces heat loss and make it suitable for energy efficient application like water purification. While sweeping gas membrane distillation, a gas flow along the permeate side carrying vapor on an external condenser. This type is ideal for separating volatile compound and application requiring high purity. While the vacuum membrane distillation, a vacuum is applied on the permeate side to enhance vapor plug. This is commonly used for industrial application requiring high efficiency and low energy consumption. Another membrane is, Another membrane is osmotic pressure-driven process. The osmotic membrane distillation utilizes an osmotic pressure differences to separate liquid component. In this process, water moves naturally from a region of higher water potential to a region of lower water potential across the membrane. The selective movement is driven by the osmotic gradients. Applications include processes like dehydration, stripping of solution, making it valuable industry requiring high efficiency and precision. The diagram illustrates how water vapor passes through the membrane driven by the osmotic pressure differences, and it's collected is permeate on the other side. Forward osmosis is driven by an osmotic pressure gradient caused by differences in solute concentration. During the process, water naturally flows across the membrane from the feed solution with lower solute concentration to the draw solution with a higher solute concentration. This method is particularly useful for a liquid concentration application as it is operated with a need for external pressure or heating, ensuring energy efficiency and cost saving. The diagram illustrates the equilibrium condition and flow, demonstrating how forward osmosis enhance concentration process effectively, and usually they use for juice concentration as well. The fabrication is a separation technique. This is another method used, which is that combined permeation and evaporation. A vacuum on the permeate side create a vapor pressure differences, allowing volatile compound to pass through the membrane is vapor, leaving less volatile component behind. This method is commonly used for solvent dehydration and water purification and organic separation, offering an efficient solution for mixture that are difficult to separate using traditional methods. Preparations ensure precise and effective separation. In this section, I will explain how ceramic membrane support are made, tested, and improved based on our study. The preparation process involves using specific material such as alumina, titania, and zirconia to create a ceramic membrane. These materials are chosen for their strength, stability, and high resistance to chemical attack. After preparations, the membrane undergoes characterization where we test important properties like porosity, strength, and permeability. Finally, I will share the key findings from our study focusing on how we improve the efficiency and durability of ceramic membrane. These steps are essential for producing high-quality ceramic membrane that can be used in water treatment and other industrial processes. The preparation of ceramic membranes involves three main steps. The first is powder formation, sol gel process, and sintering, and final product formation. In the powder formation, techniques like slip casting, tape casting, extrusion, and press-shape ceramic powder into a precursor membrane. Next, in the sol gel process and sintering, the precursor is heated to temperature over 1,200 degrees C. This high temperature is necessary for sintering, which improves the membrane strength, porosity, and stability for filtration application. Finally, the final product formation involves creating composite membrane through deep coating with a particle suspension or sol gel to enhance the surface properties. This step ensures the production of asymmetric porous and composite membrane suitable for application like water purification and industrial filtration. In our work in ceramic membrane preparation, we use key materials such as kaolin clay is a ceramic base, polyethyl sulfone, and the binders, and methyl to polystyrene is the solvent. And the tapioca starch is the pore formation, while distilled water serves as a non-solvent. The process begins with segregating and reducing the size of the clay powder through technique like ball milling, with grinding, and sonic separation. We then combine polyethyl sulfone, kaolin clay, tapioca starch, and N-methyl to perluidine, which undergoes immersion precipitation followed by sintering and to create the final membrane. This method allows us to produce durable, high-performance ceramic membrane suitable for various applications with efficient for promotion and enhance the strength. The physical properties of ceramic membrane were analyzed for quality. Viscosity of casting solution was measured using Brockfield programmable rheometers. The structure of the unsintered clay support was examined with the field emission scanning electron microscope, or SEM per se, to observe its surface in internal detail, or EFM, or EDX. Simple were cleaned and frozen with liquid nitrogen before analyzed, and these tests provide valuable insight into a membrane's structural integrity and suitability for applications. Various techniques including bull milling, ultrasonic processing, and sonic vibration were tested to reduce clay particle size. Results shows that increasing tools variables generally reduce particle size, except for the bull miller. A graph demonstrates how milling frequency, ultrasonic amplitude, and vibration affect particle size. Sonic vibration produce the finest particle, reaching 3.11 micron, increasing treatment duration from 15 minutes to 1 hour, further reduce particle size. The analysis confirmed that ultrasonic processing and sonic vibration were the most effective methods. SEM image also revealed that untreated clay showed larger, uneven particle, while particles treated with ball milling were reduced in size but remained irregular at high frequencies. Further SEM image also showed particles treated with ultrasonic processing to be more uniform, and those treated with sonic vibration were finer and more evenly distributed. This finding emphasized the importance of control processing parameters. The initial dope solution had high viscosity, leading to defects in the clay support. This was resolved by adjusting the ratio of solvent, additive, and clay powder. The final composition was 7% polymer, 47 by weight solvent, and 45% clay and 1% additive. Membrane casting thickness was controlled using adhesive tape. To avoid uneven thickness, casting was done at a room temperature and distilled water was used in the coagulation bath, resulting in membrane with higher mechanical strength and less brittleness. Increasing the tapioca starch concentration in the casting solution raised its viscosity. The graph shows the direct relationship between starch concentration and viscosity. The SEM analysis shows that if the tapioca starch concentration increase, the pore size also increase, with pore ranging from 1 to 15 micron. Higher polysaccharide content form a larger finger-like structure affecting the membrane structure. SEM image of the different tapioca starch concentration show a trend of increasing pore size from smaller uneven pore at 1% to larger well-defined pore at 4% to 5%. The graph confirms that pore size increased from 12.75 micron to 15.43 micron with a higher starch concentration. This finding underscore the importance of process optimization and preparing high-quality ceramic membrane for various applications. Ladies and gentlemen, so let us take a break for a moment to enjoy the traditional performance from the Art Academy. Please.
Hadirin sekalian, marilah sama-sama kita saksikan persembahan selingan daripada pensyarah dan pelajar aktif yang dikenali sebagai Symposium Group. Dipersilakan. Demikianlah persembahan daripada Symposium Group Astif UMS. Hadirin sekalian, syarahan diteruskan dengan menjemput semula pemidato kita untuk naik ke pentas. Dipersilakan.
Thank you very much, pengurusi saudara pengurusi majlis. I continues my Syarahan Perdana today. So now we want to talk about nanofiber is improved material. These sections will cover the rules of nanofibers and material improvement, focusing on their properties, fabrication methods, and applications. Nanofibers are transforming various industries due to their unique characteristics and wide-ranging applications. Nanofibers are the ultra-fine fibers with diameters between 1 to 1,000 nanometers and a length over 100 times their diameters. They are much smaller than human hair, is shown in the visual comparison to the pollen grain and human hair. Nanofiber are classified into first, naturally occurring, which is cellulose and fibrin, or synthetic, for example, polypropylene, polyamide, and carbon nanotubes. Blend of natural and synthetic polymers are used to customize properties for specific applications. Nanofiber membrane have several key properties. First one is high surface area to volume ratio for high absorbencies. Interconnected nanopores structure for mechanical integrity and supermolecular arrangement for enhanced properties, nano size which reduce flow resistance and increase flexibility, while tailored surface properties for hydrophilicity, hydrophobicity, or bioactivity. Nanofiber are typically made in form like membrane, scaffold, tubes, and yarn. The primary fabrication methods are electrospinning and melt blowing. Both methods are scalable, simple, and allow control over fiber formations. Electrospinnings use high voltage to eject charged liquid into nanofibers, producing uniform fibers, but challenging to scale up. While melt blowing use hot air to attitude polymers melt into fibers, ideal for large-scale production of non-woven nanofibers. A comparison shows the electrospinning produce finer fibers but difficult to scale, while melt blowing more efficient for mass production, producing slightly larger fibers. The key differences, the electrospinning produce fibers in the range of 50 to 100 nanometer, while melt blowing produce fibers from 600 to 800 nanometer, while electrospinning has the lower throughput, which is between 0.5 to 2.5 kilogram per hour, compared to melt blowing, which can produce 15 to 40 kilogram per hour. The electrospinning is more expensive, but produce high quality fibers, while melt blowing is more cost effective for a large scale production. In electrospinning, the following parameters impact nanofibers production. The first is solution. Higher viscosity, conductivity, and lower solid content improve fiber formation, while the process like voltage, flow rate, and emitter to collector distance influence uniformity, while ambient like temperature, humidity, and airflow determine the final fiber quality. For melt blowing, the key factors include melt parameters. Higher melt index and temperature improve fiber quality, while the process like matte flow rate and A improve the velocity are crucial. While ambient, secondary air temperature and flow impact fiber solidification. By controlling this parameter, high quality nanofibers suitable for various applications can be produced. One of the key advancement in nanofiber research at University Malaysia Sabah is the development of nanofiber membrane distillation for desalination. This research aims to address global issue scarcity by using nanofiber-based membrane in desalination. The schematic diagram illustrates the pilot plant setup, which integrates seawater heating and filtration system, membrane distillation modules for efficient desalination, and solar collector to utilize renewable energy. This collaborative project with Zeta Limited demonstrates our commitment to innovate solutions for global water challenge. Through our partnership with Zeta Limited, we have successfully achieved the first mass production of nanofiber, which is matte blowing equipment provided by Zeta Limited, enable large-scale nanofiber production at UMS. The image shows the matte blowing system in action and our joint effort in the lab. This collaboration enhances our ability to produce nanofiber as industrial raw material for various applications. One of the key applications of nanofiber is in heat and sound in solutions. Nanofiber welding and sheet are lightweight and effective for both thermal and acoustic in solution. This product showcases the versatility of nanofiber membranes in industrial like construction, transportation, and industrial in solution. Nanofiber material also crucial for mask and filter. One of the products, we call it Z400 face mask, available in white and black, offering advanced filtration efficiency. We also have a generic face mask produced at UMS using matte-blown nanofiber membrane, while PM 2.5 filter sheet, which specifically designed to filter particulate matter, ensuring cleaner air, because 2.5 is the most dangerous particle for our lung. So these improvements are particularly important for addressing public health need during the COVID-19 pandemic and air pollution crisis. Nanofiber also play a vital role in oil-water separation. Palm oil male effluent, nanofiber membrane efficiently absorb oil residual from palm oil effluent while not the water. The oil spill remediation, for instance, nanofiber mats effectively absorb crude oil spill from the petroleum industry. The application demonstrates the environmental benefit of nanofibers in tackling industrial wastewater and oil pollution. In this section, we explore the innovative use of membrane distillation to treat brackish water. The project focused on developing a pilot plant that uses a hydrophobic membrane to effectively filter brackish water while generating both clean water and electricity, making it suitable to promote areas lacking conventional power sources. This project offers a promising solution to global water scarcity issue using renewable energy in the process. This project also, we have a champion of sustainability winner from Malaysia and go for finalists in the Global Sustainability Award arranged by ICAMI with other company like Aramco and also the chemical company and Ottoman company and other company, which is only 6 finalists being selected for the World Championship. These projects begin with the goal of creating an integrated membrane distillation system that combines both membrane distillation and osmotic membrane distillation technology. Some challenges we encountered including managing pressure drop and pressure load along the pipeline, which required optimization during pilot testing phase. Initially started at Karambunai, the project was later relocated to Sungai Burung, Tawau in 2017. Where they continued refining the system to treat brackish water efficiently. For the membrane distillation, The core of the membrane distillation process involved the hydrophobic membranes that separate the brackish water into two streams, one being vaporized due to heating and other cooled to collect purified water. The process works by creating a temperature gradient that allows water vapor to pass through and membrane and condensate on the other cooler side, ensuring both efficient treatment of brackish water and high energy efficiencies. To begin the treatment process, brackish water was extracted using a 4-inch submersible pump located 100 meters from the pilot plant, with the pump placed above 3 feet below the surface. The pontoons was built to provide stability for the pump, enabling smooth operation and ease of maintenance. The pump's role was crucial in drawing a brackish water into a system for further purification. Once the water is drawn in, it was stored in a 5,000-liter sedimentation tank for 24 hours to allow particulate matter to settle. The water then passed through 2 sand filters and was further purified using a microfilter and heating tank before enter into a membrane distillation plant. This multi-step pre-treatment process ensured that the water was sufficiently clean before the distillation phase. The membrane modules used in the plant were carefully selected for their durability and efficiency. Made from polypropylene, these modules were 1,500 millimeter long and a pore size of 0.1 micron, offering membrane area of 1 meter square. The choice of material and module specification was essential for achieving effective filtration and ensuring the system long-term performance. A schematic diagram of the system of the membrane distillation outline how the pre-treatment process, heating mechanism, and membrane modules are arranged. The diagram also shows the flow freshwater collection system, ensuring the water treatment is optimized for maximum recovery. The layout is crucial for the overall efficiency of the system and the successful treatment of the brackish water. Throughout the project, we encountered a few technical challenges. One of the key issues was the pressure load that developed within the membrane module. To address this, we upgraded the rejection pipeline to a larger diameter to help reduce pressure and ensure smooth operation. This solution helped optimize the system performance and prevent operational inefficiency. Additional challenges include the high temperature and rejections of water, which was a hot and the feed water and uneven heating of the feed water in the solar heating tank. To resolve this issue, we implement the recycling system for the rejection water, which help distribute heat more evenly and improve the overall system performance. Additional issue arose when salt contamination across in the condensate liquid due to salt remaining in the vapor collection component. To resolve this, we use the upper outlet port of the membrane module for vapor collection. This adjustment prevented contamination, ensuring the purified water remained clean. This improvement is shown in the schematic diagram, help optimize the system operation and water quality. Moving forward, we explore the exciting potential of microalgae membrane bioreactors, or MBRS. This system presents an innovative and sustainable approach to wastewater treatment, nutrient recovery, and biomass production. They use microalgae to remove pollution from wastewater while also producing useful byproducts. In this section, we will discuss how this system works and findings from our research and the challenges that still need to be addressed. Microalgae-based wastewater treatment, known as algal remediations, involve cultivation microalgae in wastewater to remove key pollutants like BOD, COD, and excess nutrients, particularly nitrogen and phosphorus. Microalgae can thrive using basic resources like carbon dioxide, sunlight, and nutrients from the wastewater. This method is environmentally friendly and cost-effective as it uses unlimited resources. The algae biomass can also be repurposed for biofuels and other available products, making a sustainable solution for both water treatment and resource recovery. A key challenge in microalgae cultivation is managing the nutrients content in wastewater. Is not all wastewater provide the ideal condition for algal growth. The N to P ratio, nitrogen to phosphorus ratio, is crucial for determining how efficiently algae can grow and remove nutrients. If one of these nutrients is in excess, it can limit algae growth. Our research shows that when phosphorus is the limiting nutrients, growth slows down significantly, demonstrating the need for balanced nutrients level to optimize algae productivity. While microalgae systems are promising, cost optimization remains a major challenge. Operating costs, including capital investment, maintenance, and harvesting, can be significant. For biofuel production, additional costs come from the cultivation, extraction, and water usage processes. However, combination nutrient removal with CO2 captured can reduce overall costs and make this system more economically viable for large-scale use. Optimizing this aspect is essential to making microalgae system a feasible solution on the global scale. Another limitation is the risk of cultivation contaminations. Microalgae grow in an open aquatic system where unwanted organisms such as zooplanktons and protozoa can invade and compete with algae for resources. Additionally, fungal and viral infections can harm the algae's ability to grow. To address this, sterilization process are used through the increased capital cost, but ensuring combination control is crucial for maintaining the system stability and efficiencies. Microalgae growth can also be influenced by environmental factors such as light intensity, temperature, nutrient availability, and salinity. Additionally, toxic chemical in wastewater can limit algae effectiveness. Biotic factors such as presence of pathogens further complicates cultivation. Achieving the optimal balance of these factors is essential for sustained algae growth and successful wastewater treatment. Operating factors like mixing, dilution, harvesting, frequencies must also be operated to maintain system stability. Once the microalgae have treated the wastewater, the next critical step is harvesting the algae biomass. Various methods such as sedimentation, flotation, centrifugation, and filtration are used to separate the algae from treated water. In some cases, flocculation is needed to help the algae clump together for easier separation. This step is vital not only for recovering biomass, but also for ensuring that the treated water meet discharge quality standard. However, the industrial scales, the small size of microalgae cell present challenge for efficient harvesting. This slide illustrates how microalgae membrane bioreactor system operates. The system consists of several components. The first one is untreated synthetic wastewater tank. Microalgae is a photobioreactor, treated water tank, excess algae holding tank, and ultrafiltration unit. Our research shows that this system successfully reduced high concentration of ammonia and phosphate. For example, 81.9% ammonia removal and 25.5% phosphate removal demonstrate the system ability to treat wastewater efficiently while while also recovering valuable biomass. Further analysis also shows that membrane bioreactors excel at removing ammonia and phosphate, especially from lower concentration wastewater. Ammonia removal reached 81.9%, while phosphate removal reached 25.5%. The lower phosphate removal suggests it may be the limiting nutrients in the wastewater, affecting overall nutrients removal efficiency. This reinforces the need to balance nutrient level to optimize the performance of the system. The performance of ultrafiltration membrane was also assessed, and key findings should include: first, the turbidity reading were consistently below 5 FAU, indicating successful retention of algal biomass, while the COD and BOD removal rates exceed 70%, demonstrating the system overall efficiency in improving water quality. This result confirmed that ultrafiltration membrane play a crucial role in enhancing the performance of microalgae system for wastewater treatment. Microalgae harvesting involves several methods. The first, as I mentioned before, the centrifugation, flotation, sedimentation, filtration, and flocculation. For harvesting, the biomass can be converted into biofuel using thermochemicals, chemicals, or biochemical processes. Combining this method improves efficiency, which is especially important for scaling up microalgae-based system to commercial level. One of the most effective methods for harvesting on a commercial scale is flocculation. These techniques use high molecular weight flocculants to aggregate algal cells for easier separation. Both neutral and synthetic polymers are used as flocculants to enhance efficiencies. The combine of harvesting techniques illustrated here further streamline biomass recovery, ensuring better efficiency for a larger scale application. Ladies and gentlemen, distinguished guests, as we come to the conclusion to this inaugural lecture, I reflect on the journey we have shared today. Discussing how membrane technology can address global sustainability challenges such as clean water, wastewater treatment, and resource recovery. These advancements are not only about scientific progress, but also our collective responsibility to ensure they are economically viable, environmentally friendly, and also socially impactful. This progress would not have been possible without the collaboration, determination, and shared vision of many. I would like to express my sincere thanks to University Malaysia Sabah for fostering a culture of research and innovation. My colleague, collaborators, and students for their dedication. To our partner, Zeta Limited, Japan, and also Tokyo Institute of Technology, led by Mr. Mitsuhiro Takahashi, and also special acknowledgement to the team behind today's event, led by J. Darwis and his dedicated team, of course, as well as Associate Professor Dr. Fatima Ahmedi, the beautiful mile who crafted such a thoughtful and encouraging narrative for my video presentations today. Even I didn't see that video. This is first time I see it today. So I think I'm very surprised that they have crafted together with us, Steve, such a nice video. And I could say that this is the most, nice video that I ever had in my life. My gratitude also goes to the performance team led by Dr. Lillian, Dr. Oscar, and Dr. Vectors, and their esteemed colleagues, alongside the Penerbit team under Professor Madya, Dr. Kenneth Teo, for their contribution to this lecture success. A heartfelt thanks to you, to the GTMK team for their technical support, the Perhubungan Corporate team for their effort in ensuring the events outreach, and the Pejabat Pendaftar and Chancellery team for their unwavering administrative and logistic support. And of course, to my fellow researcher here, we have Dr. Zika, Dr. Cham, Sofian, and other things who I cannot list it. Actually, there's so many of them for their contribution and commitment. To the core success team, I need to also thank you for present, and you are deeply appreciated. And I extend my gratitude to everyone here today. Above all, my deepest appreciation goes to my family, whose love and support have been my foundation throughout this journey. My wife, Puan Maslipa Idris, my wonderful children, Fatin Arisa, Muhammad Fadil Zedan, and Fahim Wafi. They are behind me to support along my journey. In the words of the greatest philosopher Socrates, wisdom began in wonder. It is through curiosity and the pursuit of knowledge that we find the path to wisdom. Innovation is a journey, and each step we take brings us closer to solve global challenges. Let this lecture inspire future generations to continue building upon the foundation we have laid and strive for even greater solutions to serve humanity and protect our planet. To the younger generations, embrace the power of science and technology with wisdom. The world will serve. The future is yours to shape. Ladies and gentlemen, the inaugural lecture stand is a beacon of academic excellence, yet its significance depends entirely on us academicians. We hold the power to shape it into a reverb legacy or let it diminish into a hollow traditions. It's up to us to decide. It is therefore, let us reignite the spirit of scholarship. If we fail to honor and uphold this value, we cannot expect others to do so on our behalf. The stewardship of knowledge rests with us. For the Prophet Muhammad, PBPU said, the best people are those who brings the most benefit to others. Let us ensure our effort in academia leave the lasting impact for the betterment of the society. Thank you for your kind attentions. May this lecture spark further dialogues, collaboration, and innovation toward sustainable solution through membrane technology. Saya pun mau berpantun juga lah sikit. Di laut tenang, kapal berlabuh, setiap langkah penuh bermakna. Terima kasih atas perhatian, syarahan ini kini ternokta. Wabillahi taufik wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh. Thank you very much.
Demikianlah tadi syarahan perdana Profesor Insinyur Dr. Rosalam Haji Sarbatly. Terima kasih diucapkan. Sebelum berakhirnya majlis kita pada pagi ini, hadirin dijemput untuk berdiri bagi nyanyian lagu Bertekad Cemerlang. Dengan ini berakhirlah majlis kita pada pagi ini. Dijemput Profesor Insinyur Dr. Rosalam bersama-sama pegawai-pegawai utama Universiti Malaysia Sabah serta hadirin sekalian untuk melawat ruang pameran dan seterusnya menikmati jamuan yang telah disediakan. Dipersilakan. Music, slow down, music please.